Hey everyone, welcome to LPW Solutions. In this video, we're going to explore how deep learning can be used to detect pneumonia from chest X-ray images. We will go step by step from dataset selection to training a deep learning model and even integrating it as a desktop application. So stick around till the end, let's get started. The dataset we are using is the COVID-19 pneumonia normal chest X-ray images dataset, which is available on Menly Data. This dataset consists of three classes: COVID-19, pneumonia, and normal. However, for this project, we will only be using the pneumonia and normal categories. The dataset link is provided in the description below. While extracting the dataset, we will get three folders: COVID, pneumonia, and normal. However, for this project, we will only be using the pneumonia and normal categories. Since the dataset does not provide pre-separated training and testing sets, we need to manually create these folders. So first create a train and test directory inside a folder. Inside both train and test, create two subfolders, pneumonia and normal. Select 100 images from each category and move them to the test folder. Move the remaining images to the train folder. This ensures that our dataset is well structured and ready for training a deep learning model. Upload the dataset to your Google Drive. Make sure to organize it properly inside a folder. Next, open Google Colab and upload the notebook from our GitHub repository. Now let's break down the code step by step. This command mounts your Google Drive so that we can access the dataset stored there. Here, we import the required libraries for data preprocessing, model building, and evaluation. This sets the path to our training and testing dataset folders. We use image data generator to preprocess the image by rescaling pixel values and applying augmentations like shear, zoom, and flipping. Here we load the dataset, set the batch size, image size, and class mode for binary classification. We are using DenseNet 121, a powerful pre-trained deep learning model, and removing its top layer so we can add our custom layers. We add new layers for pneumonia detection and define the final sigmoid function for binary classification. Since we are using a pre-trained model, we freeze its layers to prevent them from being modified during training. The model is then compiled with the Atom optimizer, binary cross entropy loss, and accuracy metric for performance evaluation. We train our model using the fit function. This is where we actually let our model learn from the data. First, we pass in the train generator, which is the data we want the model to train on. Next, we define steps per epoch. This is the number of batches the model will process in each epoch. We set the equal to the length of the train generator, meaning the model will go through all the training data in one epoch. Then we specify epochs. In this case, we have set it to 5, which means the model will train for 5 complete passes through the training data. For validation, we use the validation data parameter and pass in our validation generator, which holds the data we use to test the model's performance after each epoch. Finally, we use validation step to specify how many batches of validation data the model should process in each step. This code saves the trained model to a file using save function, so we can use it later. Next, we plot the training and validation loss to see how the model improved. We also plot the training and validation accuracy to check how well the model performed during training. Then we make predictions on the validation data using predict function. This method gives us the probability that each image belongs to a certain class. To convert these probabilities into actual predictions, we apply a threshold of 0.5. If the probability is greater than 0.5, we classify it as one class, and if it is less, we classify it as other. Finally, we generate a classification report which provides important metrics like precision, recall, and FN score to evaluate the performance of the model. We also visualize the confusion metrics using a heat map. Now, let's go ahead and run the cells to see the results. After training, we can see that the model achieved a 93% validation accuracy, which indicates that it performed quite well on unseen data. Looking at the confusion metrics, we can observe that the true positive rate and true negative rate. The TPR shows how well the model correctly identified positive cases, while the TNR shows how well it identified negative cases. Both rates are high, which means the model is doing a great job in distinguishing between the two classes. I have created a Tkinder desktop application where you can input an image and see the model's prediction in real time. So let's run the application and see the results. So that's it for today's video. Thanks for watching. If you enjoyed this video, don't forget to like, subscribe and hit the bell icon for more videos and tutorials.